everyone. Hi. Thank you for staying along. It's quite late. We're all tired. So my name's Dimitris. I'm a part-time PhD student at the School of Media Arts and Humanities at Sussex University, which is in Brighton, UK. And my topic is live coding instruments. Has anyone here ever heard the term live coding before? I'm sure most people would have. Yeah, okay, live coding. And so I decided on Clojure as the main language for me to sort of experiment with and conduct research and conduct practical experiments, also known as just playing a gig with your friends. And so today I'd like to introduce some of that research, give you a little bit of context, and talk about why Clojure was the incredible fit that it has so far turned out to be. I've, like many here, I assume, I've watched a ton of Clojure videos on YouTube. I'm a particular fan of every video of Rich Hickey's I could get my hands off, and in tradition, I will first define some things that I found to be very useful terms in my research and in my way of thinking. And these three terms are kind of at the core of what my research focus is how does code result in ergonomics, ergodynamics, and ergologies? And the first two are kind of words that you are most likely familiar with. The third one is one that, as far as I know, I've come up with, but I think is a very useful one, and I think you'll agree with me. Ergonomics comes from the two Greek words ergo and nemo, and ergo means work in a kind of abstract capacity. Nomos means law, which doesn't really make a lot of sense when you combine the two, but nemo, which I think is the more likely explanation, nemo means to distribute. And so ergonomics is the distribution of work or of labor. That's how I understand it. And of course, we have cognitive ergonomics, physical ergonomics, and ergodynamics is, again, ergo, and dynamis. Dynamis means strength or potential. And so it's when you're working with something or when you're watching something sort of carry on its work, what is the feeling that you get about its power, about its strength, about what it can and cannot do? Ergology is a combination of the words ergo and logos. And logos means a lot of things, but it's most often understood to mean speech or reasoning. And so in this case, the ergology of a system would be the how and why we would reason about its inner workings. So what is actually going on, at least as far as we can tell, in the way that the system is working. And as programmers, we love black boxes. We love the notion of abstraction. We love pushing complexity under the carpet and not really thinking about how it works as long as it does. But that seems to, it has led me into a few rather unfortunate predicaments, such as spectacular crashes while live on stage, because I hadn't exactly understood how the various bits of software we're using were talking to each other and what could possibly go wrong. And so my research, specifically in the context of a live coding musical instrument, focuses on what exactly are the relationships between these three. We change the code, we change the hardware that we use to interact with the code, we change the language that we use to write the code in. It's an incredibly complex system that moves all the time and shifts and evolves. And each aspect of this triangle of kind of three aspects of interacting with that system, each change in one can affect all the others. So a change in the ergonomics of a programming language, let's say syntax or its command line tool ecosystem or anything like that, a change in how it distributes the load, whether cognitive or otherwise, that comes with working on it, will undoubtedly affect what it feels like to work with it. And therefore, this kind of continuous feedback interaction between these three terms is kind of at the core of what I'm interested in. And of course, when we're working with computers, we're interacting with them. If we're not interacting, then they're not really useful. They're not really doing all that much. But what exactly is computer-human interaction? What is it that we're actually interacting with? I'm currently interacting with a key on my keyboard, and I'm interacting with some pixels on my screen. But I'm sure we would all agree that's not all I'm interacting with. There's something a lot more going on, and some of it is in my head, and some of it is in my computer, and some of it is kind of a nebulous abstract notion. But to really understand what it is that we're interacting with when we're working with a computer, we'd have to first consider what exactly is a computer in the first place. And so I'm a huge fan of the idea that a computer is just a kind of an information machine chameleon. It's a shape-shifting, or rather functionality shifting, because its kind of shape remains pretty constant even through centuries, as we'll see in a bit. But it's a functionality shifting machine. On itself, it does nothing other than imitate whatever it is that we describe. We describe machines that add numbers, and we describe machines that filter photos, and we describe machines that synthesize music. The computer just does that one thing that it does, which is take our descriptions of those systems and just execute them as faithfully and as hopefully quickly and correctly as possible. But that's not what computing always meant. A computer back in the day was actually a human being. It was a very highly educated human being, mostly women, up until men decided that computers were too interesting and kind of pushed them away. But there were highly educated women that would do a lot of work and would think about these machines that we now offload the kind of execution of onto our computers, but they would assume that functionality of the functionality shifting kind of machine chameleon. And so I'm not really a huge fan of the term human-computer interaction, because this is what we call a computer, and this is not really what I'm interacting with. In the words of Harold Abelson, computer science is a pretty terrible name for this business, because it has as much to do with computers as biology has to do with microscopes. And so I like to think about a kind of more complex network where there's a human, there's a machine that executes the ideas, but also there are the ideas themselves. There's interaction with the imagination. There's communication with the output of the machine, and then with the inputs of the machine. And it's a much more kind of multi-dimensional and dynamic system. And one thing that has really struck me over the years is that I've been constantly on this journey of discovering more and more things that have already happened, sometimes decades ago, sometimes way before I was even born. Things that have happened and have seemingly kind of been lost in history. I remember really kind of thinking about this when I heard Alan Kay talk about how computing is one of the few fields where it's almost standard practice for people to not really dive deep into the historical foundations upon which we build. As he said, no physicist or chemist would ever graduate without knowing exactly what Einstein's or Marie Curie's contributions were to science. And yet a lot of people graduate from computer science or informatics degrees and have quite possibly never heard of Lisp, or they haven't played with a Smalltalk system, or any of these kind of brilliant ideas that, for one reason or another, and quite sadly often that reason is money, have just kind of died out. So Lisp machines and Emacs were tremendous ideas, and what I particularly love about them is this idea that we use the thing to make the thing. There's this kind of self-referential positive feedback loop where the more we build it, the more we can build with it. It's kind of like the workbench that you use to improve its own self. And when it comes to a creative practice, when it comes to making a career out of being a musician, and you do this thing 8 hours a day for the rest of your life, growth is a really important thing. And being able to see that you're growing is also a really important thing. And we want to make our instruments our own as much as possible. Ivan Sutherland's Sketchpad is also one of those things that have kind of mysteriously disappeared from modern education. At least when I was in uni, I didn't even hear a word about any of these things. And what I particularly love about this is that in its almost in the infancy of the field of computing, this was a system where through direct manipulation you would build symbolically rich structs. It wasn't just place the square here and then just kind of rasterize the thing and move on. You were building a system that you could then work with, and it was a dynamic system. It was an interactive system. It was unlike a lot of kind of direct manipulation tools that we have today, at least for music. Particularly interesting is also Smalltalk, is one of those systems that is made, when you interact with it, its ergodynamics gives you, just by looking at this, the class browser and being able to go to all the methods and change the code and kind of re-update the whole thing, its ergodynamics tell you that it wants to be played with. It wants you to get your hands dirty and get in there and start tweaking it. And this is something that I think is particularly valuable, and something that I've felt coming from Clojure as an energy more so than any other language that I've worked with. And of course, the Lisp-heritage helps, but there's also a lot of other things that that I think contribute to that. And then generally, some ideas from the past that haven't caught on as much as one would think they would, but as you can see, these are all kind of Clojure's bread and butter. It can kind of it is in a lot of ways more of a chameleon than most other languages that I've worked with, and particularly when you're trying to build a language for a very specific purpose, so a domain-specific language for performing music live. That's a very it's a very particular situation to put yourself in, because you have extreme time constraints, but also no one's going to lose their jobs if you mess something up. No one's going to lose their homes. No one's going to potentially die. But also there's extreme demands in terms of performance. You cannot drop a single buffer, otherwise it will kind of ruin the moment in the performance. There's a lot of projects today that I've kind of drawn inspiration from, and I'll kind of quickly breeze through them. MaximSP is one that you're likely very familiar with, and it has this particular capacity that most IDEs just completely lack, which is for the code itself to become an interface of itself. So you don't write the code and then write more code to create an interface for the first code. As you're writing the code, you're also building the interface as a kind of interlinked step. And then we have textual programming environments, and I happen to suffer from tennis elbow syndrome for about a decade now. So using the mouse is almost prohibitive for me anymore, and that really put a psychological curse on me, if you will, because I felt really demotivated in my ability to interact with a computer in the ways that I would interact with my other musical instruments, with the piano or the guitar, or in the ways where I could almost close my eyes and just go for it and have a feel for what's going on enough so that I can interact with it. Gibber is a textual programming environment which tries to kind of step it up a little bit in terms of dynamic visualization, and it's a domain-specific language for music, and I just love how it just kind of tries to visualize the little things that are happening in the code, because there's so many things that are happening, and if I'm gonna have the understanding and kind of balance of mind and body sometimes to be able to interact with it in real time in front of an audience, then I need as much kind of feedback as I can get from it. Fracture is one of the more interesting ones, which I assume some of you might have come across. It's a structural editor for Lisp-like languages. I think in this case it's a scheme. But this is even a step closer to kind of this ultimate promise of, can I just close my eyes and go for it? Do I need to constantly be looking at where my cursor is and kind of judging how long I need to keep the down arrow key for in order to like navigate and not make mistakes and so on? Or can I just build muscle memory? And muscle memory is an incredibly important part of performing music. You cannot be thinking about every single thing that you're doing and how to move your body to do it while you're doing it, as you're interacting with other musicians and kind of feeling the whole pressure of the stage and the audience. And so muscle memory in programming, even though we all have it in kind of small local contexts, we all have muscle memory for typing a for loop or a lambda or things like that. We don't really have muscle memory for doing bigger picture, kind of higher level things. Or at least I find that really hard to do when the way that the concrete steps in which those things are meant to be executed in are kind of fluid. They change all the time depending on what we're doing. Arena Lisp is another fascinating project that I discovered quite recently, and it just takes it up even further up a notch. And this is actually written in Clojure. It was a big part of why I ended up going for Clojure for this. And I particularly love how it's a projectional editor, and I think soon we'll see that there's the user writes the code for a ramp that will go from a value to another value over a period of time. And as the ramp is actually moving, it will visualize it as a little ramp. And then when it finally gets there, the whole thing will be replaced with the target number. So it's a live dynamic system that is connected with the actual underlying signal engine and the evaluation graph in non-superficial ways. There's a kind of very direct structural relationship between the two. SAPF is another interesting one by the creator of Super Collider. And what I love about this particularly is that it works as a projectional editor that can have multiple different syntaxes. So we can have a Python-style kind of indented syntax, we can have a Lisp-style S-expression syntax, or postfix notation syntax, and so on. It's all the same tree at the end of the day. And so it's just up to how we visualize it. I'll skip through some of these. This is a modular synth, and for those of you who've never seen one before, this costs about as much as a house, and you wouldn't really have one of those unless you're a superstar. But the idea is that this is a computer. This is an analog computing machine, and interacting with this is very, very different to interacting with a laptop. As you can kind of see here on the right, a live coding performance is very much just someone standing in front of the laptop for half an hour. And so I'm hoping to kind of slowly change all of this, and a big step in doing that is a URAC module that my supervisor Chris Kiefer and I released as an open source project this past summer, which runs a Clojure-like tiny interpreter on a Raspberry Pi Pico. And the idea is that instead of having the computer and the instrument and plugging the two together, we put the computer in the instrument, and suddenly we can start interacting with it in more ways. As you can see here on the right, you can code it through a serial app on a tablet, or you can just attach a keyboard onto your case and a screen. And then custom keyboards. This is a huge part of the ergonomics of actually playing live on stage. There's an incredibly fascinating project. I can't remember the name right now, but there's someone who wrote a whole Clojure program for customizing a 3D model of a keyboard, or generating one based on your preferences and your hand measurements and so on. And it kind of compiles it to a kind of 3D CAD programming language, but the idea is that I can use the very same language that I use to make my music in, and sometimes even the very same bit of code, to design a keyboard to then kind of go back and keep writing more of that language to keep designing more keyboards and so on and so forth. But is this idea that it's a live coding instrument and a live coding practice is as much a computational luthiering practice as it is a creative practice. We're meant to interact with these machines in ways that go far beyond just playing with them or playing them. And we get really kind of intimate with their inner workings. And of course, other kind of interfaces. But this is where structural editing comes in really important. And if we're going to be able to use interfaces like this to play music live in any kind of, with any immediacy and any effectiveness, we really kind of need to rethink how it is that we approach code. If it's just a two-dimensional grid of characters, then a joystick and a few buttons is not really going to cut it for interacting with it all that much. And finally, I want to get to the actual product itself. TimeLines is predicated upon this idea that music is just a function of time. It is physically, but it also is mathematically, or at least it can be thought of as such. And the idea is that if we have a computational process that produces sound, then every single one of its parameters can just be a very literal function of time, of just a lambda of one argument. And then by abstracting time like that and kind of modifying it in interesting ways, we can build up all sorts of kind of very, very interesting patterns. I would just like to play a very short clip of the first iteration of TimeLines, which was implemented in Haskell, kind of inspired by tidal cycles in a lot of ways. And what you see here is every synth represents just a process that keeps on running forever. And every one of the parameters, amplitude, frequency, modulation ratio, and so on, is just a function of one argument, float to float. And by passing the same value of time to all of these arguments, all of these functions, but also by manipulating the functions in such a way that they go in and out of sync and match, and by creating tension and then releasing it, essentially, we can write a lot of pretty interesting and unique music. A point about ergologics earlier. The way that version of TimeLines worked, it was a very naive decision on my part, but it would, I think every half a second by default, it would sample all of the waves, write each one to its own WAV file, and save it on disk, and then pass the path of that WAV file to the Super Collider audio engine, which would load it up as a buffer, index through it using a half a second phaser, basically the buffer window, and then apply the values to all the parameters. And the reason that I went for that was because I didn't really know how to do a lot of complex DSP programming back then, and I figured that Super Collider does a lot of work to interpolate and anti-alias and do all of these things when reading from audio buffers. And so I was hoping that I could just piggyback on top of that. And that turned out to be a pretty terrible idea for a lot of reasons. One of them being that the library that I was using to write these audio files, because I could not figure out how to write a WAV file header and body kind of manual file myself. The library that I was using for that is a C library, and Haskell had this automatic kind of way of figuring out how to use that. And then it all just kind of culminated to me being completely, well, one sec, I lost my cursor. It all led to me just kind of being completely unable to there we go. completely unable to use my live coding language. It just got to this. Bitrot eventually settled in, and I have not been able to play with that with my undergraduate kind of dissertation project ever since, because of a matter of implementation. I mean, obviously I could go in and fix it now, but that was the trigger that made me say I will just go and start doing it from scratch and do it properly this time. Whatever that means, and it's been a long journey trying to figure out what that means. I will just go back to the presentation. And actually, this is not a new paradigm. People make music by kind of drawing time-dependent curves all the time, but no one really does it with code, or at least not that I can tell of. Most music computing platforms are event-based, so it's a discrete, trigger this sound here with these parameters for this amount of time, and even though that's powerful. And it's a particular kind of ergological design choice that can come from many reasons. One of them just being performance needs to be top-notch if you're going to do completely continuous kind of sample-level synthesis. But it really forces you into a particular musical box. And so the idea was that a kind of more continuous signal-based system would provide a lot more support. The problem was with Haskell is that it was incredibly hard to do that at any symbolic level. Like, I could combine functions that do things over time, but then I could not inspect them. And because I could not inspect them, I could not write kind of creative functions that would do things to my musical patterns based on how they actually worked. It's one thing to have a function object, it's another thing to have the entire source code for that function. And so with Clojure, I decided to go a very, very different way and do everything symbolically, at least as long as possible before we actually have to just compile the lambda and evaluate it. And so this is the core of the signal data type. It's a very simple one. It just has a lambda expression and a boolean of whether it's constant or not. And then while I was trying to kind of wring my brain to figure out how to make useful functions that do things on this, I realized that it's functional programming is this thing that over the years I grew slightly warmer to, but at first it seemed like really foreign and alien and also just unnecessarily abstract, at least for my purposes. But then I realized that a function of time is kind of like a bifunctor. It is a functor of two types. The input type is time, and then the output type is whatever value, whether it's a signal of strings or numbers or whatever. But a bifunctor has two ways that you can modify it. You can modify the one thing, or you can modify the other. And in this particular case, it just means, am I applying a function to the output of a signal, or am I applying a function to the input of that signal? And so after many, many more hours of just trying to figure out what the hell to do with that piece of information, I figured out that with the implementation of this one function, bimap, which takes a function and potentially some arguments for pre and one for post, and then just extracts all the signal functions, checks to see which one's constant, combines them all, passes time to the right things, and does the whole kind of chain processing. This is 80% of the logic of how this system works in this one function. I didn't have to write many, many different separate, completely independent implementations of a function to slow signals down and another to modulo them by 2, or it's the power of abstraction that kind of condensed everything into this one idea, with the tricky part that it took me a while to wrap my head around, that the functions that we apply to the inside of the signal are functions that go from expression to expression, not necessarily from a value to a value. And so with a little bit more code, that allows us to lift and lower signals. To lift just means to take a value and return a signal that always returns that value. And to lower means to take a signal function within the context of a relative time, whatever that means, and to just kind of try and sample that and bring it back down into a value. And eventually we get to the point where we can do, I'm just going to write some random code here. We have a signal t, and t is the simplest signal that we can possibly have other than a constant signal, which is just a function that takes time and just returns it as it is. In this particular case, it's just the identity function, so it doesn't have to be time. It can just be anything. And then to lift post, in this case, post just means to apply it to the output of the signal after it has been sampled rather than to the input or something else. To lift a function such as, let's say, plus, will give us back, in this case, an opaque function. We can't really see what this function does, but that's okay because that's not really what that function is there for. If we apply that to a signal, then suddenly, you can't really see that all that well, but if you look at the bottom, we just get back another function of time, which just applies the addition operation. In fact, I can just provide more arguments here. It will just apply symbolically. It won't actually run anything. Apply whatever that function was to the result of potentially lowering one of the arguments, or one or more of the arguments, if they're signals. And so, even though this is a very early stage and a work in progress, I've been running a few experiments with using this as the basis for everything in the app. So whether that's the audio, whether that's the GUI or kind of anything else, I am trying to see how far we can push this idea of everything being a function of time. And of course, how do we, a function, a particularly function like that is an immutable object, but when we're interacting with a system, we are changing things. So the obvious way to go about it here is to just replace one pure function with another. And so we have a sine wave that does the same thing forever, but a few seconds in we change it with a square wave, and suddenly we've created an evolving pattern instead of just a continuously repetitive sine wave. But then that also just kind of misses the point of helping our computers help us by allowing them to understand what it is that we're trying to do. And instead, what if, instead of replacing a function with another, what if we took the function that was already there and modified it at the moment that we know what the next function is going to be? So whenever the event input comes in from the user, what if we just modified it and made it such that it almost kind of assumed that it always knew that at that moment it would have to change into something else. And so we still have a functional an immutable kind of underlying representation that completely abstracts time, but every single modification that we make to that along the way gets clipped on as a sort of history of changes of sorts. And then ideally at the end of a half an hour live coding session with such a system, I'd like to be able to serialize a data structure, deserialize it, and pass time from 0 to 30 minutes, and recreate the exact same behavior of the program, sonically, visually, and otherwise, as if all of those things were kind of already baked into the timeline, so to speak, of the function. I would like to invite. Ooh, if I can find my cursor again. This is just a rough visualization. I was hoping to have an interactive visualizer that I could demonstrate all of these things today, but I've been debugging like crazy for weeks, and we're close, very close, but not quite. But this is the idea: is that we can just create the functions that do a lot of things and then combine them. This is the bread and butter of programming, right? We have a function that always does this and another that always does that. I'd like to invite you to completely scrutinize and destroy the terrible code that I've written in this repo. And inspired by this morning's keynote, I will not go back home and remove all the terrible stuff that I've left in there. I will instead just leave it there, because that's part of the process of building a system. And I'm sure a lot of you will be surprised or not to find code that you've written used in this project, but I would be much more interested to have people start adding code to the project. But this is an abstract project almost. It doesn't need to be this particular implementation. It's an idea. It's about how we can abstract time and relationships between time-dependent values in a way that will allow our computers to help us work with these ideas. It's about not so much interacting with a computer, but using a computer to help you interact with what it is that the cognitive artifacts, which is a term that I really love, helping ourselves interact with our ideas is what I think computing is about. And as far as I'm concerned, Clojure has done an incredible job at kind of staying out of the way, but always being there when I need to do something as crazy as monkey patch every single function in a namespace to operate on signals instead of straight values. So thank you to Clojure, and thank you to the organizers, and thank you to all of you for listening.